All right, so we know trigonometric waves are pretty much the building blocks of our digital world, right? But what good are building blocks if you can't move them around? We've already figured out how to stretch and squeeze them. In this explainer, we're going to learn how to shift them up, down, left, and right. Let's get into it.
You know, this quote really says it all. We've already mastered changing a wave's shape using amplitude and period. Now we're going to learn how to literally pick that wave up and put it anywhere we want on the graph. This is how we make these waves actually model what's happening in the real world.
So here's our game plan. We'll start with the easy stuff, the vertical shift, which we call the midline. Then we'll get into the trickier horizontal shift, and I'm going to show you the #1 trap that almost everyone falls into. And finally, we'll put the whole shebang together and see how these tools let us model the world around us.
Okay, first up is the vertical shift. Honestly, this is the most intuitive, most straightforward move you can make. It's all about just moving our wave straight up or straight down. Let's see how it works.
The core idea here is really simple. The vertical shift is controlled by just one value, which we call d, and we just tack it on at the very end of the function. This d value gives our wave a new horizontal center, which we call the midline. You can literally think of it as the wave's new sea level.
Let's look at a quick example. The function y equals sine of x minus 4. It does exactly what you'd think it would. That minus 4 at the end grabs the entire sine wave, which is usually centered right on the x-axis, and just drags it down 4 units. So the new midline, the new center of that wave, is the line y equals -4. Simple as that.
All right, we've moved up and down. Now for the horizontal shift, which also goes by the name phase shift. And I'm going to give you a little heads up. This one can feel a little backward at first.
So the phase shift is all about that side-to-side movement, and it's controlled by this value c that's hanging out inside the parentheses with the x. Now, the crucial part here, the thing you have to burn into your brain, is the standard form. Notice it's written as x minus c. That minus sign, that's the key. It's the source of almost all the confusion. So getting this right is everything.
And here it is. This is the counterintuitive rule that you just need to memorize. Because the formula is based on x minus c, a minus sign actually moves the graph to the right. So if you see x minus pi, the wave shifts to the right by pi. And yeah, that means a plus sign moves the graph to the left. Why? Well, because x plus pi is really the same thing as x minus negative pi. It's a little weird, I know, but you have to lock this in. It's essential.
Okay, now let's talk about the single biggest mistake people make with phase shifts. I call it the common factoring trap. Pay super close attention here, because once you see this, you'll be able to spot it and avoid it every single time.
Let's look at this function. Y equals the sine of 2x minus pi. Okay, based on what we just talked about, that minus pi looks pretty tempting, right? Your first instinct, your gut reaction, is probably to say, oh, the shift is to the right by pi. But is that correct? And that is the trap. It looks right, it feels right, but I promise you, it's wrong. And the whole reason it's a trap is because of that little 2 that's multiplied by the x inside the parentheses.
To find the real phase shift, there is one step you can never, ever skip. You must factor out the coefficient of x, that b value, from both terms inside those parentheses. So here b is 2. When we pull a 2 out of 2x minus pi, what are we left with? We get 2 times the quantity, x minus pi over 2. Now, and only now, is the function in that correct x minus c form. And we can see the true shift is actually to the right by pi over 2, not pi.
Okay, deep breath. We've handled the movements. We've sidestepped the big trap. Now it's time for the fun part. Let's put it all together. We're going to combine all 4 of our parameters, a, b, c, and d, to build a function that actually models something in the real world.
So if someone gives you the characteristics of a wave, like, say, the daily temperature cycle, we can actually build its equation from scratch. It's like a recipe. First, you use the period to figure out your b. Then you just assemble all your parameters, a for amplitude, b for period, c for the phase shift, and d for the midline. Finally, you just plug them all into the standard equation, and boom, you've built a perfect mathematical model. And this right here is why this stuff is so powerful. I mean, think about the temperature over a 24-hour period. The average daily temperature, maybe it's 70 degrees. Well, that's our midline. That's D. And the hottest part of the day isn't right at the start. It's delayed until, say, 3 p.m. That's our phase shift, C. The swing from the morning low to the afternoon high, that's all about the amplitude, A. And the fact that this whole thing repeats every 24 hours, that gives us our period, B. Every single parameter has a tangible, real-world job to do.
You know, what's truly incredible is that this is just scratching the surface. This whole principle of shifting and stretching waves is the foundation of a huge idea called the Fourier series. It basically says that any repeating signal, any signal, from the sound of a guitar string to a Wi-Fi signal, can be perfectly recreated just by adding up a bunch of simple sine waves. This is how we digitize and analyze our world. It's the absolute bedrock of modern signal processing.
So this leaves us with a final question for you to think about. We've talked about temperature and tides, but now that you have these tools to precisely move and shape any wave you want, what other cycles out there could you start to model? Think about patterns in biology, in the stock market, or even in our own daily habits. The periodic world is all around us, just waiting to be described with math.